The purpose of this video is to do a quick walkthrough protein purification simulation program. You can use a free online version at eggboost.com, or you can use a free download with some limited capabilities. So we're going to start the program, and at the start choose a mixture, and we're starting with EZ3 mixture, okay, protein 1. So we have some information about it. It's active at wide range of pH values and for a few hours up to 40 degrees Celsius. So protein you want to keep cold when you're working with it. At the beginning we have 30 mg of protein mixture, 2000 units of enzyme activity, and we're going to see how to purify protein 1. So on SDS-PAGE, we can see two bands. Looks like we have a 40 kilodalton and a 20 kilodalton proteins. And if we do 2D page, we'll see that there is actually a mixture of 3 proteins. So our first question is, which protein is the one we want to purify? We can use immunoblot, a technique that allows you to visualize interaction between specific antibody and the protein that antibody targets, and we have an antibody against protein 1. Here's our spot. Right, so from here we know that we need to separate protein 1 from 2 contaminants, and the most salient difference between them is in the size. This one is 40 kilodalton, both of the contaminants are 20, so we should be separating by size. What separation technique allows us to separate by size? Before we can move on, we need to hide the gel. Right? That's going to be gel filtration or size exclusion chromatography. And we can get a little more information about different columns available. I would think of these as sets of 3. Depending on the media for the beads, you can have dextran, polyacrylamide agarose mix, or purely polyacrylamide gels. And let's just, for simplicity, focus on a set of 3, say, in the middle. Ultragel ACA 54, 44, or 34. The numbers actually refer to percentage acrylamide and agarose. So Ultragel ACA 54 has 5% acrylamide, 4% agarose. What you'll notice is there's a narrow range of sizes between 6 and 70,000 daltons. And there's broader one, 12,000 to 130,000, 20,000 to 400,000. So for proteins that are 40 and 20, we should probably use ACA 54. So I'm going to choose that, say OK, and voila, we got 2 peaks. Right? Then our first thing is to check which peak contains our protein. On gel filtration, we have first fractions coming off on the left, last fractions on the right. So would larger protein travel faster or smaller protein? Right? We're going to expect that the larger protein comes out first because it spends less time inside the beads. Right? It's partly excluded. All right, so next let's see if we can figure out which fractions we should pull. So I'm going to start probably around, say, 38, and just assemble a bunch of fractions. Just to be sure, I'll add fraction 69 to see what's in this peak. Say OK. All right, and so we can see the protein we don't want, the small one, is in fraction 69, right? And fractions between 39 and 51 all contain the protein we want. Great. So we could pull these fractions. So we can now pull fractions 39 through 51. All right. So what we can see is the protein amount got reduced by 2/3, down to about 10 mg. Right? But the enzyme units are nearly all recovered, 99% yield. So the fold enrichment here is 3-fold. That's pretty good. Next, we're going to try doing this for protein 2. If you ever try a step and it doesn't work, keep in mind you can always go to abandon this step and continue and redo that step. But we're going to start over. We're not saving anything. We're going to go to the same mixture and now choose protein 2. Okay. So we got some more information about it. And let's go straight to 2D page. We know this is protein 1. We need to know which protein here is protein 2 because that's the one we can purify. Right? Immunoblot is going to tell us. Oh, there it is. All right, so we need to separate this protein from two contaminants. One has similar pI, the other has similar size. We already know that ACA 54 column, gel filtration column, can separate 40 kilodalton protein from 20. Right? So really the challenge is how to separate these two proteins for us in order to purify protein 2. Right? So they have difference in pI. They are going to have difference in charge at some pH. And that's what we're going to work on next. Let's figure out what kind of column we need. And for that, let's review the columns. Right? So an ion exchange has a positively charged column, and we bump things off that positive column with negative ions or anions. And conversely, true for cation exchange. Okay, so what we know about our mixture is sizes and pIs. So next, let's think for a given chromatography, what pH buffer should we choose? Right? So if we tried cation exchange chromatography, column negative, protein positive, at what pH would these proteins bind the column? Right? And ideally, we want protein 2 to bind, but not protein 3. So at pH below 7.5, our protein gains extra protons, becomes positive, right? At pH equal to pI, net charge is 0, and if the pH goes above the pI, then protein loses protons, becomes more negative. So here's our answer. We should choose some sort of pH that's above 6.2, so protein 3 doesn't bind, but below 7.5 so that protein 2 can bind. So let's say we try pH 6.8. Here's our prediction. Next, we're going to try that prediction out. So first, we gotta hide the gel, then go to ion exchange chromatography. We'll try CM Sepharos and elute with salt gradient. Okay, we're going to try buffer 6.8 and salt gradient between 0 and 0.5 molar salt. Oh, great. We got two peaks. One of these peaks is a double, right? So UV trace here plotted on the left shows us which fractions contain the protein, and then this pink line shows us concentration of salt, right? So we can see that there was no salt added, so that's our flow-through volume, and there's one peak there. Can we guess which protein didn't bind? We're going to expect that it's protein 3, right? And then we started to increase salt, and somewhere around here, around 0.2 molar, we had the doublet peak. Okay, so we need to sample the fractions to see which of these proteins is ours. Could you predict whether ours runs in the front or in the back? That's going to be a little tricky, right? Because we're not separating by size, it's by charge. So we're going to sample one of these peaks, say fraction 20, just to see what was in the flow through and if we lost any of our protein. Okay, and then we're going to add these fractions. I'll skip a few. So fraction 20, that's the flow through, has a small protein, as we guessed it was protein 3, most likely. Then from fraction 63 through fraction 66, we have protein 2 in a pretty pure form, right? But then after 66, our protein 2 will also have some protein 1 mixed in. So if you wanted pure protein, you would pull fraction 63 through 66, but then notice that you will lose quite a bit of activity here. If we wanted to verify by immunoblot that we got the right set of fractions, here it is. All right, and so let's see if we can pull fractions. Okay, so we recovered half of our activity in terms of enzyme units, and we got threefold enrichment using this method. Okay, so next I want you to think about a couple of questions. One is, we didn't get very good separation. We had to lose half of our activity because those fractions were contaminated with protein 1. How could we improve separation of the two peaks? Could we use different column conditions, like different pH buffer, or different dilution? For example, use pH or shallower salt gradient. So play around, see if you can get better separation so you can get more recovery or better recovery. Also, could you purify the same protein, protein 2, using anion exchange chromatography? For practice, specify column, pH of the buffer, and elution conditions, and see what you can come up with. All right? If you do that, you'll be ready for more complex mixture. The next thing you want to try is default protein 1. Good luck.